All right, so got a few questions this morning. One's regarding questions, so are all organic questions. So the first one here is regarding question 56, and this is kind of an odd one because I don't remember selecting one about chirality, so most likely this is going to disappear from the homework grade. But it's asking about splitting pattern of this compound. With HA, HB, HC, and then we have the NH3. And so you're given four options here. HA and HB are split by the 5 hydrogens of the aromatic ring. HA and HB are split into a quartet by the NH3, and then again by HC. HA and HB are split into doublets, and these are again split by HC, and HA and HB split each other into quartets. So, as far as splitting patterns go, you can actually answer a lot of this by process of elimination. You can't split further than an adjacent carbon, so only hydrogens here and hydrogens here can give rise to the splitting pattern. So the first comment that it's being split by the aromatic ring, that's incorrect. You can't be split by these because they're simply too far away for the measurement. You can't be split by the NH3. So the one about, are they by the 5 hydrogens? Nope, they're not adjacent. Quartet by the NH3, that doesn't make any sense because they are, the hydrogens and the nitrogens are actually 3 atoms away, 1, 2, 3. So if we had a carbon and a nitrogen, yes. So if we had something that looked like this, these could split each other, but these are too far away to be split. So that eliminates that possibility. And so now you're left with two. HA and HB split each other in doublets, and these are again split by AC, and HA and HB split each other into quartets. So you can get rid of the quartet hypothesis by the fact that a quartet of a quartet is actually 16. That number doesn't make sense. And then if you have doublets split into doublets, so doublet of a doublet of doublet, that's 8 peaks, and that's what you see are 8. So you don't actually have to understand fundamentally about anything about NMR. You can do this by process of elimination. But let me give you a little bit more complete explanation as to why the answer is they each split each other into doublets. This is why we try to stick away from chiral compounds, because even though these two aren't chiral, this center is. And because it is chiral, this nitrogen and this hydrogen are going to have opposite effects, are actually going to have a splitting effect on the HA and the HB because they have different, these two have different magnetic environments relative to this HC. So this one is trans, it's on the opposite side from the HE, this one's on the same side. So because there is an asymmetry in the magnetic field, these two look differently. They have the same chemical shift, but they end up splitting each other. And then you have the adjacent hydrogen, which ends up splitting those further. So this is why we really try to stick away from chirality when it comes to discussing the NMR of molecules, is simply it's a bit too complicated for an Orgo 1, Orgo 2 course. This is something that you would kind of cover in a higher level NMR course. If you take like a graduate NMR course, you would talk a lot more about this. Or honestly, you just use software to figure it out. But odds are I'm probably going to get rid of this question. This was not a question I would have picked. My guess is that McGraw-Hill has updated their test pool, and so this is the question they're going with. But yeah, you can do it by process of elimination, but as far as fundamentally determining like how HA and HB and HC affect each other, it's outside the scope of this course. We're not going to worry about worry with chiral molecules. Next question, can we go over the two optical activity problems? Volume of solution for cholesterol and intimate purity for morphine on the test packet during the live stream. So let me bring up those problems. So for cholesterol, the problem in the table, we're really going to work with here. Alpha equals alpha D times L, and concentration is going to be grams over volume times the EE over 100 because you're being asked to solve for the volume. So if I rearrange this equation, I get volume equals alpha D times L times G times EE over 100, all divided by alpha. So alpha D you're given in this problem as negative 31.5. You have an optical rotation alpha of minus 36.1. Mass of substance is 0.978. The volume is unknown. The path length is 3 decimeters. And the EE in this case is 22%, or when you divide it by 100, you get 0.22. So let me bring up Excel. And equals negative 31.5. I feel like I got those numbers flipped. Nope, 36.1. That's a pretty concentrated solution. So if you're getting 0.562, that's correct. I think there's just a typo in the key. But yeah, the volume here is 0.562 mLs. That kind of an odd problem. Odds are that's just kind of a holdback from an earlier draft. But yeah, if you're getting the 0.562, you're correct. It was probably supposed to be an optical rotation, honestly, of 0.361, and that would have given you 56.2 mLs, which would have made a lot more sense. And the morphine. Yeah, the morphine's another one that's looking like that was supposed to be 0.523 and not 52.3. But let's work it out anyway. So for the morphine, you're asked to solve for the EE. So if you rearrange this top equation, you get alpha times 100 divided by alpha D times L times G over V equals the EE. You're given the alpha here as minus 52.3. The alpha D as minus 132. Path length here is 2 decimeters. And we have 0.224 grams dissolved in 11.3 mLs of solution. So if I work that out, actually getting 9.9, getting about 10%. So when I do this, I actually get, just keep in mind, this is already in percentage. So I'm getting 9.99 trailing on. That's already the percentage. You don't multiply by 100. So that's my guess for that one. You're getting the 999.3 because you're multiplying by 100 to get percent. This CE is already in percent. So when that 9.99 is not, this is already 9.99%. You don't have to multiply it by 100. Problem 2 on page 15 of the study guide. All right, you receive a sample of camphor for the manufacturer. You want to figure out if it's actually pure. And so for this problem, you measure the alpha A, and this is given to you as 7.08 degrees. The alpha D for camphor is 44.26. That comes from the table above it. You're given a path length of 20 centimeters. This is 2 decimeters. And you're dissolving 1 gram in 10 mLs, and you're looking for the EE. And so for this problem, several previous live streams, what you get is an EE of 80%. But this is just algebraic rearrangement. It's similar to the one that I've just solved. All right, so that's it for the questions I've gotten asked. And correct, so you weren't supposed to multiply by 100. That EE is already in percent. And if you're not working in percent, then you just get rid of that 100 that's in the denominator. But yeah, that's actually where that 100 shows up in that formula, is converting from percent back to just a normal, like, decimal point. Yeah, and that would be your instinct if you're saying, like, here's percent. This formula does a lot more hand holding in that regard, so it's definitely there to ensure that your final answer is already in percentages for you. Yeah, so that 100 gets you back to percent. So if it helps you out when you do these types of problems, the alpha is alpha D times L times C times EE divided by 100%. All right, so that's it for questions this morning. Again, I got the chat open if you've got any questions. So to clarify, that formula, if you're trying to convert percentages before you put it in the formula, so that would be your instinct to take like 99% convert to 0.99, that formula doesn't make you do that. That formula lets you plug in the 99% directly into it. So we've never been multiplying. When we've been multiplying and dividing by 100, it's purely come out of this formula. So our percentages are showing up as a result of this 100. But we haven't been multiplying or dividing by 100 to get back and forth to percent. We've been using this 100 in the formula itself to make that type of conversion. So if you've been using this formula, you're just explicitly plugging in EE. We're just not converting EE as a percentage. So if you were given, like, your sample was 92%, and you were to stick it into this formula, you would stick it in as 92, you would stick it in as 0.92. If you were to stick it in as 0.92, we would get rid of the 100 here. And so we would just have EE if you're going to do this for any types of percentages. And vice versa. If you solve this formula and you want to get it back to percent, if you were going to just go ahead and multiply by 100 anyway, you would leave the 100 out of the formula. So when you rearrange this problem to solve for EE, get alpha D times L times C. When you multiply by that 100, that's how you get back to percentages. Answering this question is about 2 weeks ago. So there's definitely like 4 live streams where I go through how to do that type of NMR. I would recommend starting with a carbon 13 and then working your way down to the 1H NMR. The big thing with 1H NMR is looking at multiplicity. You can tell from the multiplicity, you don't have to know anything about the chemical schists to know where the 1H sits, because there's 4 unique splitting patterns in that molecule, and that's how you identify the hydrogen. So for the 1H, you don't even have to worry about where the chemical schists would lie. And the integrated area is kind of a nice backup scenario. Well, actually, yeah, I take that back. There's 3 unique splitting patterns. There's the triplet, there's the singlet, and then there's the triplet of a quartet. The triplet of quartets uniquely define the 2 triplets. Yeah, the 2 triplets. If you look at their integrated area, that will tell you which hydrogens they correspond to. The carbon-13 is the only, there's one that has an area of 3 that uniquely defines it as the methyl groups. The others you have to arrange based on what you'd expect based on the number of carbons they have around them and the types of carbons they have beside them. So that carbon that has 4 carbons bound to it is going to have the most deshielded peak. The methyl group in the end is going to be the most shielded, and that just leaves you with the 2 in the middle to kind of figure out. Yes, because there are 2 sets of hydrogens that are adjacent to two hydrogens. So if you have a bridging CH2 group, that's inherently going to give you triplets on anything that's adjacent. So you should have 2 sets of triplets because you're going to have two sets of hydrogens that are, well, the carbon-13 is the easiest. And that's not to disparage what you're doing. Like, it's just carbon's so much easier because there's no J coupling. Hydrogen, if you have a model, can be easy with J coupling, but the issue with J coupling is like going the other way, trying to backtrack from the structure what it is without a model. So nucleophilic addition of HCN to a carbonyl. So let's just take a generic carbonyl. We're not going to specify what R and R prime are. They can be hydrogens, they can be carbon groups, but we're going to limit ourselves where R is either carbon or hydrogen. So with the HCN, it's a weak acid and it's going to dissociate into H plus and CN minus. So for the nucleophilic attack, easiest way to look at this is to look at where the charges are. So oxygen is more electronegative than carbon. And so this delta here represents partial charges. We have a positive charge on the carbonyl and we have a negative charge on the oxygen. So our cyanide contains a lone pair on the carbon and we have a hydrogen come out of it. So what will happen is we'll get the carbonyl here to attack. We'll get the cyanide, the carbon on the cyanide to attack the oxygen. This will kick us up, and our first product here is the alkoxide. The alkoxide is then going to attack the hydrogen, and this will give us a tertiary alcohol and a cyano group. So the trick with cyanide is, remember, the lone pairs are on the carbon, not the nitrogen. And actually, that's kind of a weird thing that pops out of molecular orbital theory. I shouldn't say weird thing. It's explained a lot better in molecular orbital theory. Nitrogen does have lone pairs, but they don't participate in these types of reactions. Also, because you do a carbon-carbon coupling reaction, this is irreversible. So normally we'd have reversibility errors written here. We don't get that with carbonyl chemistry. For right now, you're focusing on the overall concept. As we start moving into the functional groups, we're going to emphasize the NMR a lot more. So there are lots of potential peaks in the NMR. There's lots of overlap, and you haven't worked with like alkenes enough to understand like the sp2 hybridized carbons, what that's really telling you, and the sp3, sp2 hybridized oxygens. So right now it's more understand what the concept can tell you, and then as we start getting into more, as we start specializing in these functional groups, we start going through the alkanes, the alkenes, the alkyl halides, the alcohols, the alkynes, the ethers. That's when we're going to start saying, okay, for the ethers you would expect this particular bending mode, and we'll do a few problems where you look at where that bending mode should be and what you would expect to see. For this course in general, we focus more on the functional group range. We don't care so much about the fingerprint range. We don't use the databases, but that's what you would do in practice. And what you would do in practice is that if you were synthesizing a compound and you would say, okay, I think I'm synthesizing ether or an aldehyde or a ketone, you would try to see if that peak appears in your final product. So you never would approach IR completely with no information going, well, what is this compound? The packets are actually pretty poorly representative of that. What you would generally do is that you would have a guess, and then you would see if the guess is consistent with the IR, and then you would back it up with the fingerprint region. So again, for this test, we're much more focused on just what does IR tell you? What can it tell you? And then as we start getting into later tests, then we'll start saying, okay, you did the synthesis. Does the synthesis work? Because things like alkanes, you can actually get multiple different products. And so you would need to know, like, okay, so something like permanganate can create ketones, aldehydes, and alcohols. Those are all very different bending modes. Excuse me. So for the alkanes test, I could give you a compound and say, okay, here's an alkene we reacted with permanganate. What was the actual final product? And you would just go, okay, well, I know it can be an alcohol, an aldehyde, or a ketone. And you look at the IR and say, okay, it has the alcohol bending mode. I must produce the diol or produce the ketone. Yeah, the packets, there's no good way to kind of like ask you those types of questions right now because you simply don't know enough. So it was more kind of getting you just an exposure to like what does an iron spectrum look like, kind of getting you going through those tables. But again, as we start getting to actual reactions, this is where we're going to start like looking at the IR as a diagnostic tool. Okay, a solution containing 60 grams of ethylene glycol and 250 grams of water is collected minus 10 degrees Kf for water. The amount of water separated as ice. That is an interesting question. So we're going to have to make an assumption here, and the assumption here is that none of the ethylene glycol falls out of solution. So the formula here is delta T equals Kf times I times the molality. And the molality here is the moles of solute divided by the kilograms of solvent. So I'm going to represent this as N over M, or N over Kg. So the delta T is negative 10. The Kf here is 1.86. For organic molecules, the I is going to be 1. We have 62 grams of ethylene glycol, so you need to convert that to moles of ethylene glycol. And then you would solve for the kilograms of solvent. So you get the Kg equals negative, or 1.86, and sorry, the delta T isn't negative, times 1 times your moles of ethylene glycol all over the 10. This is how much was used to dissolve the solvent. So whatever mass you get here, you're going to subtract that from 250. So 250 minus, and you need to convert this to grams, that'll give you the grams of water that's frozen out. Yeah, I should be moles of ethylene glycol. If it's 1, then it's just times 1. So your kilograms here are 0.186 kilograms. That's 186 grams. So 250 minus 186, that gives you 64 grams of H2O that was frozen out. So this delta T here is going to fix how many moles of solute you had, because or moles of solvent, kilograms of solvent you had. And from there, that'll tell you how much water wasn't used in making this solution. All right, so back to J coupling. So the way we teach NMR here is that we teach it to go take a model, build it, and predict what you'd expect to see, and then compare that to a data table. So if we look at the NMR of this problem, if I just kind of gave you the spectrum and told you to go backwards, in principle, you could get this structure back from the 1H Nmr. The problem is that it's a lot of work, and there is no uniqueness theorem. So for this, there's only one spectrum you can generate. But as far as going backwards, that one spectrum could correspond to a lot of hypothetical molecules that we just aren't clever enough to build. So, for example, I could build I could build this molecule, and the 1H Nmr would give me the exact same answer as this molecule. I've just kind of added a carbon in there. So it's not useful to go backwards from the spectrum because, again, there's no uniqueness for the spectrum back to the molecule, but there is a uniqueness theorem for the molecule to the spectrum. So what's easier to do is to take a starting guess and go from the starting guess and say, okay, based on what I think I have, what should it look like, and compare it to the NMR. And in this case, you've been told this definitely corresponds to the NMR. You just need to figure out which parts correspond to what. So a few things we can look at are areas and splitting patterns, because this is an alkane. They're all going to have similar chemical shifts. This has an area of 9 because there's 9, 3, 6, 9 hydrogens. 2 here, 2 here, and 3 here. So if you look at the NMR spectra, what you'll see are those areas, 9, 2, 2, and 3, and there's unique numbers. So there's only one peak corresponding to 9. That has to be the NMR peak corresponding to these hydrogens. There's only one peak with an area of 3 that has to correspond to that particular set of hydrogens. So the only ambiguity here are the 2. So this is where we're going to start looking at J coupling. And with the J coupling, these are singlets. And the reason that they're singlets is there's no hydrogens on this carbon. This one, if we look over, it sees 2, so this ends up being a triplet. This 3, we can use this as an independent confirmation, sees 2 beside it, and so this ends up being a triplet. This one sees 2 beside it, so there's a triplet, and it sees 3 beside it, so there's a quartet. So we can tell these two apart purely by J coupling. We're going to have an area of 2 with a triplet, that's this carbon, and an area of 2 with a triplet plus a quartet, it's going to be that particular carbon. And the one that we assigned to this one because it had an area 3 should also be a triplet. So you can do all of this without looking at the spectrum. You can say based off of where the hydrogens are, what they're adjacent to, what their areas should be, and what their splitting patterns are, and then you go to the tables and say, okay, what kind of matches up with this? And we're not going to do like super big complicated molecules just because those are just tedious and time consuming. If you can do it at this level, you can probably do it for a much bigger, much more complicated molecule. And again, we're going to kind of stay away from the cyclic molecules and the chiral molecules. Chirality creates an asymmetry. You start creating a lot of unique hydrogens that don't look unique when you draw them. In fact, I'm trying to start making videos now to talk about the complexities of cyclic hydrogen NMR. What we have drawn up here is a very idealized version of the molecule. There's a lot more going on with linear molecules and branch molecules. A lot of complications average out, but when you start going to cyclic, because we don't have those conformations because of the ring, things don't average out, and you start having hydrogens that all have the same chemical shift, but because they are not equivalent underneath the magnetic field, they end up J coupling with each other or other atoms. You do basic Nmr problems are the ones that get in depth with the rings get me thrown off a bit. What would be the best approach to solve some problems? We're going to stay away from rings, and if we're going to do rings, we're typically going to limit ourselves to carbon-13 Nmr because the carbon-13 Nmr is not going to have these complications. So cyclohexane, you would expect to have a single peak. And that statement is true. If we look at cyclohexane, it has one carbon-13 chemical shift and it has one hydrogen chemical shift. And the carbon-13 Nmr, because there's no J coupling, you just see one peak of relative area 1 because they all look the same. So why doesn't the hydrogen have a single singlet? Why is it actually like a doublet of a doublet of a doublet of a triplet? Well, that's because this isn't true. What it really looks like is this. And we'll talk about this in the next chapter when we get to alkanes. So we actually have what's called the boat conformation. And the boat conformation, where are you, creates two different types of hydrogens, axial and equatorial. This is where a modeling kit comes in real handy. You need to give me just a minute to build the almost done. Okay, so to explain why we get a multiplet in 1H Nmr. So my cyclohexane here, the black atoms here are the carbons, the blue and the white here are the hydrogens, and what you can see is that I got two sets of hydrogens. I got those that point up and down. These are my axial. Then I had the blue that kind of stagger around the ring. These are the equatorial, and these can interconvert. I can flop the molecule around, and I can make all the blues point up and down, and I can make all the whites equatorial. So, if you draw a quartet plus a triplet peak or anything similar to that, generally what I do is I take the most complicated one and draw that first. So if you've got a triplet and a quartet, I would draw the quartet first, and then split each of those into triplets. Honestly, it's a lot more complicated than this because it depends on who's got the bigger J coupling constant. So if your triplet has the bigger J coupling constant, you draw that first. If the quartet has the bigger J coupling constant, you draw that first. You're still going to get these same relative shapes, but honestly, if you were to look into the NMR itself, so let's say you had, we'll do a singlet for reference. So let's say I have a singlet with area 1, just a hypothetical molecule. Your triplet of a quartet would barely show up in the spectrum. So it's not so important that you be able to draw it so much as you can identify it. And you'll see this with a lot of these spectra. Like these multiplets, the things that are like something of something or something of something of something or something of something of something, something like there's a whole bunch of splitting patterns, just kind of all get buried down because there's a finite area associated with each peak. And in order to get all those peaks in there, you got to cut the area of each individual peak down. So you've got a triplet or quartet, that's 12 peaks. You take an area 12 and area of 1 divide by 12. So this has an area of 1, and it's on scale roughly with height. Each of these has to have an area of 1/12. Anyway, so we have two sets of hydrogens, axial and equatorial. So let's say we want to focus on one particular atom. And these can interconvert. Like we can definitely pop the ring around and get the axials and equatorials to swap places. So we only really have to look at one hydrogen. So let's take a look at this axial hydrogen. So under NMR, this axial sees three different types of hydrogens. It sees more than that. It sees these two that are not the same as at NMR because this points up in the magnetic field, this points down. So it's going to J-couple with this. It's going to J-couple with the hydrogens that are beside it because since they are perpendicular to the magnetic field versus in line with it, they experience the magnetic field differently. So there you've got a triplet. You've got a triplet from these two because they're oriented differently in the magnetic field. These two axials don't have any effect on this hydrogen because they are pointing in the same direction as the magnetic field. So actually by rotation, these are connected. it J-couples with this hydrogen because it's going in the wrong direction. So there's a doublet, and then it J-couples with this one, which gives you an additional doublet. So with the ring, even though there are all the same hydrogens by symmetry and rotation, they don't experience the magnetic field equally, and so they end up J-coupling. So you have one chemical shift, but it's a one chemical shift that J-couples with itself depending on how that atom is aligned relative to the ring and therefore to the magnetic field. So again, I'm looking to put a video about this in about a week or two. We're not going to do, if we're going to do any NMR of cyclic molecules, they're going to be incredibly simple and probably sticking just to the carbon-13. Their only exception to this is benzene rings, and that's because benzene rings are actually pretty easy to work with. So with benzene rings, we don't have axial and equatorial. Everything is in plane with the ring, and so we start recovering this symmetry under rotation. Hello. So with benzene rings, everything is trigonoplanar, and we get rid of these axial and equatorial, so the splitting patterns get a lot easier. But you can still get self-coupling. So you can definitely get these hydrogens in a ring and they'll start coupling with each other. Even though they have the same chemical shift, because they have a spatial orientation relative to each other in the magnetic field, they end up J-coupling with themselves. So to assuage your concerns for the test and for most problems, we're not going to really focus on the 1H NMR of rings. If we do, they're going to be incredibly trivial problems. It's really the NMR of linear and branch chains. Those are the ones we're more interested in because they're the ones you can actually solve. The reason why you get away from the complications associated with rings is that because rings can't rotate carbon-carbonyl single bonds within the rings, so those hydrogens actually have unique positions. With a linear molecule, they're floppy, they dance around. Because they can rotate, a lot of things average out. Sure, which NMR problems do you want to do? page 58. Okay, so 58 is really not representative of a test problem, so we'll get that one off the bat. This is much more designed for an in-class discussion, and this is kind of setting the stage for what you're ultimately going to be able to do in this course. So you're given 4 pieces of NMR, or 4 pieces of information. You've got a carbon-13 NMR, a 1H NMR, an FTIR spectrum, and you've got the mass spec. And so from these 4 pieces of information, we can infer what the structure is. Now again, in practice, you typically don't do this. You have a pretty good guess as to what you're starting with. But we're going to start this out pretty simple by saying, okay, what do we expect? What would be consistent with this? So from the carbon-13, we know that we have 4 carbons with 4 unique chemical shifts, 210, 38, 30, and 9. These 2 are definitely alkanes, or these 3 are definitely alkanes. This one is heavily de-shielded. There could be a lot of things that give rise to this 210, but typically what we're looking at with a shift that far downfield is something bound to oxygen. It's a carbon bound to oxygen. If we go to the 1H NMR, we know that we have 3 hydrogen-containing functional groups, and with their areas of 2, 3, and 3. So this is from their areas, and from their splitting patterns, we expect to see for the area of 2, it sees a chord set, so it's got 3 neighbors. So we're going to use N here, 3 in here for the neighbors. Our singlet has 0 neighbors, and our trip are 1 here with 3 and has 2 neighbors. So there's 2 that see 3, 3 that see 2, and 3 that don't see anything. Well, off the bat, you know, if this is all the hydrogens we have, these 2 must be coupling each other. So we've got a carbon with 2 hydrogens coupling to a carbon with 3 hydrogens. And there's some R group here connected to them that doesn't contain any hydrogen. So this can't have any hydrogen. And we've got a CH3 group here that's attached to an R group with no hydrogens because it doesn't split. So now we go to the, what's next? The mass spec. So the big thing with the mass spec here is that parent ion mass, and the parent ion here is going to have 72 AMUs of mass. Well, let's look at what we have so far. We know we've got a CH2 group, those weigh 14. We've got a CH3 group that weighs 17, and we have another CH2 group that weighs 17, and we've got another carbon up here which we haven't accounted for. So our CH3 here is going to give us 15 AMUs. Our CH2 group is going to give us 14 AMUs. Our CH3 is going to give us 15 AMUs, and we've got one more carbon here we haven't accounted for. So we got one at 210 that apparently has no hydrogens because we've only got 3 carbons that actually contain hydrogens. So we're just going to add the carbon in there, and that gives us 12. So if I add these up, I'm going to get 58 AMUs. So far, based on the 1H and carbon-13, I've accounted for 58 AMUs. The remaining 72 have to come from somewhere. We know it's not hydrogen because we're missing it. And the best guess here is oxygen. So if we add an oxygen, 16 AMUs, it would all add up. So if we look at the FTIR and we start going through the spectrum, there's actually a sharp peak there about, looks like 1700 wave numbers. Because our peaks here at 3000, that choppiness that precedes it, those are all alkanes. We don't care about that. But that 1700 is a really strong and unique peak, and it corresponds to a carbonyl. So a carbonyl would explain why we have a really de-shifted carbon, because carbonyls are really de-shifted, or really de-shielded. It would explain where our oxygen goes, and it also explain how we have this carbon here that doesn't have any hydrogens on it because it's busy being occupied by oxygen. And we know that we've got an ethyl group and a methyl group. So the easiest solution to this problem is this structure here. So this structure would give us the carbonyl stretching mode. It would give us 4 peaks, 210, 38, 30, 38, and 9. It would give us our splitting pattern. So there's our singlet, our quartet, and our triplet, and would give us 72 AMUs. So this is what you would do in practice. Of course, you would probably have some starting reason as to why you think this is what it is. But this is how you can take these 4 pieces of information and kind of bring them together and start estimating. Again, this is much more, these last 2 problems are much more kind of setting you up to see, like, ultimately this would be the end goal for your understanding. That you can kind of start inferring a lot of information from what's been given to you. But that's how you approach that problem. And again, there's only one on there. This is much more meant for in-class discussions, just to get students thinking forward about the rest of the course. A simpler NMR problem. So let's say we have this molecule, and we're going to start enforcing as much symmetry as we can to eliminate chirality. So if we look at the structure, we want to know the carbon 13 and the 1H and what we'd expect to see. So by symmetry, these are the same. These are the same. And these are the same. So we have an A group, a B group, a C group, D, E, and F. So in the carbon 13, we're going to expect to see 6 peaks. We've got, if you look for CH3s, that would be the A and the F groups. For CH2s, we've got the C and the E groups. For the CH, we've got D, and for the C with no hydrogens around it, we've got B. So we expect B to be all the way down here with an area of 2. D to be down here with an area of 1. C versus E. E is closer to a methyl group, so we expect C to be down here with an area of 2. E to be up here with an area of 1. And then A and F, A is bound to the most D-shielded carbon, so we expect to see the A with an area of 6 and the F with an area of 1. So this qualitatively, this is what we expect to see. We see an area 2, 1, 2, 1, 6, 1 with this progression of B, D, C, E, A, and F. So what about the 1H NMR? Well, let's build a table. So first of all, we expect them to follow kind of the same pattern with their chemical shifts. So for the 1H, from highest chemical shift down, we're just going to list the carbons. So B, D, C, E, F, A. B doesn't have any hydrogens, so this leaves us with D, C, E, F, and A. So what about the splitting patterns? Oh, sorry, I got A and F flipped. Well, A is going to be singlet. They're all by themselves. So we expect to see a singlet. So we got the J coupling. Well, okay, let's just do the area first. And then the J. So at D, we expect an area of 1, carbon an area of 4, E area of 2, A an area of 18, and F with an area of 3. Now in terms of their J coupling, we just look at what's beside them. So A is the easiest, there's nothing around it, so these are all singlets. F, there's 2 adjacent on the E, so that would give you a triplet. C's are adjacent to 1, so that gives them a doublet. E is next to 3, so there's a quartet. But it's also adjacent to 1, so you'd see a doublet. And then D, it's going to see 2 here, which will give it a triplet. And then it's got 2, 4 here. This will give us a pentet. So for the 1 H Nmr, what we expect to see is a triplet plus a pentet for D, which is just going to be a whole bunch of scribbles. Next one up, we expect to see a doublet for C. For E, a bunch of nonsense for the quartet plus the doublet. For A, this gigantic singlet. And then for F, this triplet. With respective areas of 1, 4, 2, 18, and 3. So in terms of building these predicted tables, my best suggestion is write out a list of which ones you think are unique carbons, do their areas, and then just look at them one by one. Look at the A's. Is there anything adjacent to them? It's a singlet. C, there's one adjacent. That's going to be a doublet. D, there's 2 up here, 4 down here. And just start working through that way. And I'm curious, what does this look like if we simulate it? And the other issue is, like, because right now we're simulating so many alkanes, they are definitely going to be, all the spectra are going to be kind of like stuck on top of each other. Oops. There we go. So yeah, if I simulate this spectrum, oh my goodness, it's taking a while. So what if you get one of the shifts arranged differently in the way they are similar? If they are very similar, that's fine. The chemical shifts, particularly with these like CH3, CH, CH2s, it's not particularly easy to sit back and say, you know, it's definitely going to be higher or lower. This is kind of a qualitative assessment. And definitely with this molecule, the chemical shifts are all going to sit between 0.5 and 2. So it's great that I've drawn it out really blown up like this, but imagine that all of this compressed in a super teeny tiny range. And if there's any type of serious J coupling, like, you're just not going to be able to resolve any of it. So if you're qualitatively kind of getting the shifts off, that's fine. The point is that you're not like saying, oh, this is definitely more shielded than F. Like, that's qualitatively wrong. But if you're going to sit back and say that, well, I expect kind of this progression, but maybe these two are flipped, you're fine. You clearly understand the concept. It's just that it's a really big, complicated molecule. There's probably little nuances that go into it. There we go. So to show you like the reality, so I've drawn this nice picture down here. These are all spread out and really easy to see. But let me switch you to the desktop where I've actually simulated it. And this is the spectrum. You can see that a lot of things sit on top of each other. And when this program's counting the integrated area, it's counting these all as 21 hydrogens because it can't possibly like resolve any of this. So it's great that we've kind of drawn these idealized spectrum, but there's a lot of noise buried down in here because of all the splitting patterns. Oh man, especially when you start stepping up the resolution, it's just going to look like nightmare fuel. So yeah, when we start, if I were to stick something in there like a couple of fluorines, it would help clear up the spectrum. It would help spread things out. But even then, like, if we start building really complicated molecules, the reality is those peaks all sit on top of each other. That's why programs like NMR database exist. The Bohr model sometimes say the electron does not lose energy while revolving, but how is it true as circular motion is accelerated motion? So the Bohr model in itself is inherently incorrect. And the Bohr model was meant to kind of explain why you see these patterns in the periodic table. So why, when elements bind, you expect to see 2, 8, 8, 18, 18, what's the next one? 32 electrons in the outermost. You always end up getting this thing where the atoms tend to end up with this many valence electrons. And so when we look at the Bohr model, it was a very qualitative model, which is why it disappeared. So the actual model that works is what's called the Schrodinger model. And the Schrodinger model says that really electrons exist as probability waves. And we describe that probability with the wave function psi. And psi is the probability of finding the electron. And there are 4 numbers which are referred to, hey, welcome, I'll see you Wednesday. There are 4 numbers which refer to the particular wave function you end up getting. So if you look at a p orbital, the electron actually exists in 2 nodes. It's not going around in a circle so much as it is there's a probability of finding it. And because the electron is so small, its energies are quantized, meaning that it can only gain or lose energy in discrete values. And so it can't lose energy, otherwise it would, yes. So this is when you start getting into quantum numbers. And so when we talk about the Bohr model, we're not actually referring to actual orbits. It's not turning around in a circle. These just simply refer to distance from the nucleus and energy. And so this is what Bohr envisioned with his model, was to say that they're like planets orbiting the sun, but they're not really that. And in order for them to go from one orbit to the other, they have to lose a discrete amount of energy corresponding to that transition. So it's whatever light's gained or absorbed. So these are not so much orbits as they are solutions to an equation that governs this type of physics. So basically, atoms exist within, these represent stable solutions for the electron, and this isn't radius, this is energy. Oh, that pin's finally dead. So here, this isn't radius, this is energy being expressed on the r-axis. And the further away you are from the nucleus, the higher in energy you are. So he never meant to say that this is like they're literally rotating around it. They just kind of exist in stable solutions around the nucleus. The better way to represent the Bohr model is actually with this type of diagram. To say that you've got energy level 1, 2, 3, and so forth. But the big issue of the Bohr model was it was a qualitative model, and it's what's referred to as an empirical model. He couldn't prove anything with it. It relied entirely on experimental data, and because it relied entirely on experimental data, he couldn't make predictions with it. It would only work if he fit some variables to it and made it work. So what we see is the Bohr model kind of perpetuates about 1910. It'll give rise to the Lewis model of bonding. But quantum mechanics, quantum theory, quantum numbers, that's what starts showing up in the 1920s, 1930s. And this is where we start seeing a better description of what the electron is doing. All right, so that's the end of my office hours. Again, if you have any questions, please feel free to email them in advance. Organic folks, I'm waiting to hear back, but you will hear back by the end of the day as to what room we're doing the exam in this Wednesday. And I will see y'all tomorrow on live stream, and then Wednesday in person if you're an organic.